Good afternoon. Welcome, everybody. Thank you very much for coming. Hope you're having a fantastic PDC. My name's Jan Gray. I'm an architect. I work in the office of the CTO on programming models for concurrency. This talk is an introduction to programming with concurrency, and it has three themes. The first is that concurrency is becoming increasingly important for building applications and services and libraries that are responsive and that have high performance and that are scalable to the coming era of multiprocessor computers. The second is that you can get started today writing multi-threaded programs using multiple threads, shared memory, and locks. And the bulk of the talk talks about the concepts for doing that and some rules and best practices to succeed in that programming model. The third part of the talk is about how Microsoft is really excited about these coming high-performance multiprocessors. They're going to be on every desktop, and how we're evolving our programming model to improve the platform, the languages and libraries and tools to make it easier to harness these multiprocessors. The outline follows those three themes. We'll explore why you would add concurrency to your software. We'll look at how you succeed with concurrency programming today. And we'll look at some ideas and some evolving technologies for making it easier to use concurrency in your software. So first, why would we add concurrency to our software? The first reason is for responsiveness, to build applications and services and libraries that don't block, don't hang up, remain responsive to its clients, leave clients in control. The second reason is to add parallelism and scalability to your applications, which is increasingly important as the processors change to be multi-core. And the third is because certain situations induce concurrency into your applications. For example, if you're a web service responding to several clients at the same time, or if you're receiving multiple UI events, or you're a main thread of a managed code process, but there's also a finalizer thread running alongside you. Why not add concurrency to your application? What's hard about it? The main problem is it brings non-determinism to your program. When you had a single-threaded program, it starts at the top, runs through its inputs, and gets to the bottom, and every time you run it, you get the same answer. In a multi-threaded program, different schedules of the threads can surface race conditions in your code, and that can surface bugs in your code, and they can be hard to surface bugs, hard to test for, etc. So to succeed with concurrency and multi-threading, you need to understand the concepts and the issues, and you need, as you're programming, to use a certain extra discipline beyond that when you're writing single-threaded code. So these days, all applications are becoming network applications in some sense or another. Increasingly, as we add calls out to web services, or we go to files that happen to be on the network, or we talk to devices that are intermittently connected. We need a way to deal with the new challenges of those libraries that we're calling. They have different latencies than when everything used to be on the one machine. It can take longer to find out that they're failing. You have to wait for a timeout. The latencies can be unpredictable as the server loads change. And so you end up having to reflect that in the user's programming, in the user's experience. So for example, how are we doing today? We have lots of applications on Windows where they're great most of the time, and you do some innocent operation, and all of a sudden you get a wait cursor, and the machine blocks, and the user doesn't know what to do. Should I wait this out? Can I cancel it? Oh, I can't even do that. The only thing I can do is kill the application. Indeed, as we've improved the reliability of applications on Windows so they don't crash so much, hangs are becoming just as prevalent and disruptive to users as crashes are. So we need to use some new ideas to get rid of these problems. Oh, I'd like to announce that there's an overflow in room 511AB. Thank you. Okay, so what do we do to make our apps more responsive with concurrency? The key idea is to decouple as much as possible the UI and the work, so that the UI can remain responsive to inputs like cancel, even as the work runs on some other thread. As you do this, it's also interesting and helpful to reveal some of the internal states of the computation to the user and to display partial results as they become available. For example, when you're using a web browser today and you type on the address bar, go to this URL, down in the status bar you can see it resolving the address, connecting to the server, pulling down the page. And as a user, you can use that information to decide if you want to wait this thing out. You also see that these applications that reveal this internal asynchronous state machine have a cancel option. So the user is in control to say, oh, stop doing that. Once you've done this decoupling, you can also start to exploit both pre-computing of results and kind of post-computing of background work. So you can render the next page while the user is looking at this one, so that when they do a page down, they get a really snappy answer. Or you can do some work in the background after the user has issued the command. A common example is doing printing in the background. When you do that, though, it's important that you carefully look at all the new states that your application can go through. What happens if you started background printing and then you decide to close the application? You have to give the user control to say, I'll let the printing finish, or cancel the printing, I really want to stop the application. Similarly, down a level or two in your software, you want to make your libraries that you're using more responsive. So all those same ideas about exposing internal states. It's kind of in tension with the old data abstraction and transparency that we like to have in a library, for a library to expose some of this internal state. But particularly for long-running or high latency or variable latency operations, you do want to expose that kind of state. And it's important that you, of course, document the safe threading usage of your libraries, and that you're careful to look at how the libraries that your code is consuming use threads. In some cases, you can use a library that, unbeknownst to you, has some thread affinity issue. It has to be called on that thread, or problems like that. So let's have a demo here. I have a fairly simple application that we will evolve through the course of the talk. The application is to count the primes. How many primes are there less than 100,000? So we run this in theory. Okay, F5 is not fine. Is it the fabulous F-lock key? There we go. I hate these keywords. Okay. Run it on that keyboard. So we run this, and indeed it says there's 10,000 primes less than 100,000 or so. What about, often what happens is we test our application for a certain workload, but then in the field the users give it a different workload, and then unbeknownst to us, it has some responsiveness problems. So now I said, tell me the primes less than 10 million, and the thing is blocked. And I say, oh, I wish I didn't have that many primes. Oh, the application's locked up. It's not responding. And the only thing I can do is kill it. Okay, so how do we make that a more responsive application? So here, I've modified that application. I've added a cancel button, a progress bar, and this background worker component that I'll talk about in a minute. So now, when I run the application, I can see its progress, and if I give it an input that's too large, I can give up on it. I can cancel it. Great. And even while it's running, I can shut it down and that kind of good stuff. So what's going on behind the scenes there? Well, first of all, this background worker is a new feature in .NET Framework 2.0 that makes it easy to have some of this background work decoupled from the UI. It's got these three events: to do some work, to report a progress changed, and to report that the background worker has completed. And we'll see how we wired that up. First, when you click on the Start button, it runs background worker.runWorkerAsync. And that has the effect of delivering a do-work event on another thread than the UI thread. And here we handle that, and we do the count primes call on another thread. When that result comes back, we package it up in a result that will then be delivered on the UI thread. And here, that event handler, runWorkerCompleted, is run. It gets this event, and it unpacks the result and posts it in that text box. In addition, I've added a cancellation facility so that when you click on the cancel button, it uses the background worker cancel async method. And what that does is it changes a field on the background worker, cancellation pending, to true. And your background worker can poll that state to see, is the UI thread asking me to stop? Should I early out from the computation? I've also added a progress indicator, and again, using the background worker report progress method, you can report this percentage of progress. And that ends up being another event handled on the UI thread, the progress changed event, which then updates that progress bar. Okay. So let's talk a little bit about what was actually happening in those two examples. First, in the example where there was no responsiveness, the UI message queue is, when you do a user input event, a mouse click or a key press, those events go into the UI message queue and they are pumped. While the UI is idle, it pulls these messages out of the queue and dispatches them to an event handler which handles the event, such as shown in these little rectangles. When I clicked start, I started this long-running count primes computation. And while it was running, there was no pumping of the UI. And so all those inputs that I gave were blocked. In the second example, using the run worker async on the background worker object, that work was farmed out on another thread and run there. Now, I didn't explicitly create a thread. Underneath the hood, the background worker uses a thread in the thread pool to do that work. And I'll talk a bit more about the thread pool later. While that's running along, every once in a while, it posts a progress changed event, which is delivered on the UI and pumped here and updates the progress bar. And similarly, at the end of the computation, we deliver a run worker completed event to the UI thread. And so during the whole computation, the UI is live and responsive. Okay, now I'm going to talk more about concurrency for performance, for parallelism, and scalability on multiprocessors. Why does this matter? Well, we've actually entered the multi-core processor era, and we've done it about 2 years ago. So this chart shows the glorious last 30 years of Moore's Law. And back in the 70s, we had 1 megahertz processors, and they were little 8-bit guys. And all through the last 30 years, the number of transistors on a die has doubled about every 1.5 to 2 years. And also during that time, the clock frequency of the processors has also scaled up nicely at about the same rate. Now, you may have noticed in the last 2 years, processors seem to be stuck in the 3 gigahertz-ish range. And the bad news is that they're going to be stuck, they're going to be improving much more slowly than they used to. We're no longer going to get that Moore's Law doubling of processor speed that we enjoyed. The number of transistors on the die will continue to double. And the semiconductor industry roadmap shows that it will double about every 2.5 years for a long time, for at least another 12 years. So we're going to have lots and lots and lots more transistors. But the processors themselves aren't going to be getting faster as at faster rate. And this statement's a little oversimplified, but the gist of it is that from now on, for the rest of the computing industry, whatever that means, your processors don't get way faster each year. You just get more and more and more of them. And we'll talk a little bit about why that is so. So when we make chips, they're fabricated at a certain line width of the transistors in the wires. And we're currently at a 90 nanometer node. And in the next 5 years, we're going to go through 2 more nodes at 65 nanometers and 45 nanometers. And each time that happens, we can approximately double the number of transistors on a chip. And those transistors get faster, which is fantastic. Unfortunately, the interconnect between the transistors gets kind of relatively slower as we bring the line widths down. And also, our processors are already kind of maxed out on their thermal envelope. Around 100 watts per chip is about all that we can cool. So those two effects are causing the rate that we speed up the processor clock to slow down a lot. What you do get, though, is lots more transistors. And that's going to be manifest typically in PC processors as having more processor cores on a die and more cache on the die. I think it'll average out to about the same amount of cache per core as you get now, but you'll get more and more and more of them. Maybe 2 this year, maybe 4 in 2 years, maybe 8 in another 2 years, and so on. Besides the fabrication improvements, there are also computer architecture advances that we'll also be enjoying. I think that you'll see processor vendors add multi-threading or continue to have multi-threading in their parts because that lets the cores have better latency tolerance to memory. I think that you'll see the design of the system be more optimized for overall throughput, particularly for server processors, than just for single scalar performance on one sequential program. And we've already seen in the embedded systems world that when you go to integrated system on a chip, you end up having lots of cores, lots of high-speed on-chip interconnect, lots of shared cache, on-chip I/O, and DRAM controllers and stuff. So the whole system gets better, even though an individual core isn't going to be doubling to 6 and 12 and 24 gigahertz like they used to. It also means that the old world where a PC had one core or maybe two is over. There'll be a proliferation of different chip topologies. So somebody might have a laptop with 2 cores, which is sometimes one of them is powered down. Another guy might have a desktop machine with 8 cores, and they'll all be running Windows client down the road. And so as software developers, you're going to have to cope with that broader spectrum of machines that your software runs on. I'm really excited about this future, and if you look out, out to 2015, you end up with some incredible numbers on the performance of the chips. Even in the Windows Vista lifetime, you're going to have desktop machines with maybe 4 cores or maybe 8 threads, maybe more. On the server, where you already have 4 socket machines, if you think about putting 4 cores per socket or more, you end up with a lot of computation available, even on commodity cheap servers. So that means that for all of you in the room, there's some great opportunities for new kinds of killer apps. We can move beyond the apps that we have now and harness hundreds of gigaflops for new problems, games, media, machine learning, that kind of stuff. Really exciting opportunities. And I claim that the chip vendors can and will give us as much hardware concurrency as our software can absorb. If our software is still 1 and 2 threaded software, they're not going to go and give us an 8-core or a 16-core machine. So it's really up to us to write applications that can take advantage of the multiprocessors. Now, before we start talking about going parallel, as an old CLR performance guy, I want to point out that there are easier ways to make your application go faster than parallelism. The first observation is that a lot of our apps today aren't even CPU bound. They have responsiveness issues and they block, but if you look at the CPU indicator, it's at 5% or something. So I think as we improve our applications to be more responsive and to let users launch more work concurrently and so on, that can give us a chance to chew up more CPU. And when your applications do get CPU bound, you really should look at your algorithms and your data and do those optimizations first. And only when you're stuck is parallelism more of an option. You can get a many-fold improvement with an algorithmic improvement or by using data in a less inefficient way. Whereas if you have a parallel program, it's only going to scale up over the number of cores that you've got. So the mantra we had in my CLR perf talk here 2 years ago was to let your perf goals and your perf measurements be your guide. Take the data measurements and then see where the hotspots are in your code and optimize them until they're good enough. However, there's no denying that every 2 or 2.5 years or so, you're going to get twice as many cores, and so are your competitors in the software business. So you want to figure out how you can take advantage of that over time. And I've got a couple of references here with some really good information for speeding up managed code apps. Okay, so now we're going to talk about how you can take advantage of concurrency and parallelism today. It turns out there's lots of different parallel programming models, and some of them are more or less appropriate for different settings. The easiest one to think about taking advantage of is on the server, where you've got lots of client work coming in, and you can afford to give those client units of work to a thread each. And it's a very nice model. You just write your code linear on your thread, top to bottom. To the extent that you share memory, to the extent that you share data with other threads, you try and keep it in a transactional shared store like a database, and let its concurrency control take care of your concurrency issues. It's a very nice model. Also, when you write, moving to the next one, when you write SQL code, that's actually kind of a declarative parallel operation. And indeed, on a big database, your SQL query goes to a parallel query optimizer, which on your behalf figures out how to allot it amongst your 4 or 8 or whatever many cores. As I mentioned at the start of the talk, we often see some kind of induced concurrency in your programs for various reasons. If you have programs that are for loops or do loop kind of parallelism, we already have a nice solution shipping in Visual Studio 2005, which is our OpenMP support. And there's a great article by Kang-Soo Gatlin in the MSDN that you've got in your briefcase that drills into that. Another popular kind of parallel programming model is message passing, and MPI is popular, and C omega and CCR I'll talk about briefly at the end of the talk. We're also looking a bit at implicit parallelism over functional languages. It's very nice in a functional language where you don't have assignment, you can easily farm out sub-expressions to different processors. That all said, the dominant client parallel programming model today is multi-threading, shared memory, and locks. And so we're going to drill into that one and figure out how to write correct programs in that model. So I have 2 slides of concepts I want you to be familiar with. Since you have multiple threads of control, and each of these threads is touching data, it can happen that memory that you're sharing with other threads changes out from under you. You observe other threads' changes in a surprising way, or other threads observe your changes. This is only a phenomenon for memory that you're sharing with the other threads. So globals, static fields, and those heap objects that you've decided to share. You have also your private data, which includes your program counter, your registers, locals, your thread local store, and those heap objects that you have not exposed to other threads. Your manipulations of that data is thread safe already. So there's 3 key isolation techniques that you have to think about in your multi-threaded programs. The first is confinement, sharing less of your state. Is there a reason this sub-object under my object needs to be seen by the other threads? No. Well, I won't give them a pointer to it, and I know that they won't be able to touch it. Immutability is a technique where if you're building some data structure that you're going to share, if you can possibly build it in a read-only way, or never update it in place, but only update new read-only copies, that means that the other threads and you are not going to be confused about your access to that shared memory. The final one, the one in the end you can't avoid, is needing to synchronize your access to your shared state. To the extent that you and another thread are manipulating some shared state, you need a mechanism, which is usually called locks, to serialize your access. So only one of you is touching that shared state at the same time. And I've got a simple example here. Thread 1 and thread 2 are racing to touch A or data from reachable from A. And thread 1 tries to lock A, and he wins the race. So he gets in and he holds the lock. Thread 2 loses the race. He's going to be blocked until thread 1 lets go of the lock. And then thread 2 will go right in, take the lock, and do his work. Second set of concepts I want to talk about are more about making sure your multi-threaded programs remain correct. In multi-threaded programming, it's more important to be aware of the invariants that your program has. Those properties that must always remain correct. In a single-threaded program, your invariants only have to be correct when you've returned from the data structure. But in a multi-threaded program, any time another thread might get a peek at your data is a time that those invariants have to hold. So you're going to have to wrap serialization, that is locks, around any manipulation of your invariants. There are 3 really interesting concepts in this multi-threaded space: safety, liveness, and efficiency. Safety is generally this property that your invariants hold from the start of your program to the end, and you get correct results, independent of what order the threads are run. To the extent that your code is sensitive to thread ordering, then you have a race condition violating your invariants, and that leads to really hard to debug bugs. It's hard to test your code too. You have no confidence that when your code runs correctly on the 1 processor machine, it'll still run correctly on the 4 processor machine. Liveness is this property that your program continues to make progress. It doesn't get stuck. There's a phenomenon called deadlock, where you have cycles of threads waiting on each other. And I've got an example here where thread 1 gets in and acquires lock A, and concurrently with that, thread 2 gets in and acquires lock B. Unfortunately, each of them needs to acquire the other lock, and so that's a cycle. Neither of them will finish their computation and release their lock, so neither of them will ever make progress. I think these bugs are easier to deal with, though, because you could see the deadlock in the code. Your program has stopped. The race conditions are more subtle. The third aspect I wanted to talk about was efficiency. That is that on an 8-processor machine, you're making good use of all 8 processors. And it's interesting that these 3 concepts are in tension. It's easy to take a single lock and lock all of your code with that one lock. That will give you safety and liveness, but the efficiency will be poor because only one thread can work on that data at the same time. To the extent that you add more fine-grained locking, then you start having the risk of deadlocks or the risk of broken invariants. Another concept in multi-threaded programming is waiting. It's not always the case that you have a lot of threads and they're all running full out. Often you have a thread does something and then has to wait for another thread to establish some condition. And there's no point running it at all until that condition is established. And 2 examples of this are a producer and a consumer. The consumer should just wait until the producer has produced some work for it. And similarly, a manager launches a bunch of workers. He's going to wait for all the workers to report back saying they're done before he proceeds. So to summarize these concepts, here's how sequential and multi-threaded programs contrast. And this table is taken from a great article by Vance Morrison a few months ago in MSDN. There's a reference to it at the end of the paper. In a multi-threaded program, as we've said, the memory is constantly changing out from under you to the extent that you're not looking at it under serialization of a lock. So locks are essential. You have to actually think about what your invariants are and how you protect them from other threads. To the extent that you have composition of some work between 2 data structures, you may have to put a lock around the whole thing so that someone doesn't see some intermediate state between the 2. And as soon as you have more than one lock in your program, you can get to this deadlock phenomenon. Okay, now we're going to talk about the actual APIs that you'll use in managed code to write some multi-threaded applications. The first thing you're going to need to do is start up some concurrent activity. The best way to do that, I believe, is to use the thread pool and call QUserWorkItem, giving it a delegate to call back on some thread pool thread. We saw the thread pool earlier in our first example. It's really a nice facility in managed code because it will adaptively tune to the number of processors you have and to the kinds of workloads you're doing. It will start up more threads if more threads would help, and it will spin down threads if you don't need that many running anymore. It also helps amortize the cost of starting up threads across a whole lot of work. Sometimes, though, you need the actual control of starting this thread or that one, waiting for it to finish, etc. So there are, as a secondary thing, we have these explicit thread management APIs. When you start thinking about using them, though, it raises the question of how many threads do I need to start, and all these kinds of questions. And generally speaking, you'll be happier using the thread pool. It also means that you can share that resource with other workloads, possibly in your process. The next category of work you're going to need to do is doing this locking to serialize your access to objects. And in C#, there's a lock on object statement. In Visual Basic, it's sync lock. It's syntactic sugar for these 3 statements. I want to enter a monitor, which I'll talk about. Then I want to do my code serialized with respect to other threads, and then I want to exit the monitor. A monitor is kind of like the old phone booths with the folding doors. Several people can get to them, but once one goes in, nobody else can enter the phone booth until that other person leaves. Then the third category of things you're going to need to do is put a thread to sleep waiting for some other thread to establish a condition. And one way to do that in managed code is to say monitor.wait, and then to wake up another thread who's waiting to use monitor.pulse or pulseAll. You'll use these operations from inside a lock block. So you'll say lock on some monitor, you'll test your condition, and then you'll say monitor.wait. That has the effect of releasing the lock and putting you on a queue of waiters And conversely, pulse will have the effect of taking you off that wait queue and making you runnable. You'll still have to reacquire the lock, which happens transparently, as we'll see in some code examples. So the next few builds of this slide talk about some rules for using these facilities to write correct multi-threaded programs. The first is that for all your writable shared state, you must access it under a lock. And always use the same lock for a given piece of data. So I have here some code that in the single-threaded world was just fine. When you add an item to the collection, it sticks it in the last element and increments the end of the pointer to the end of the collection. In a concurrent world, let me go back there. If this was executed concurrently on several threads, all kinds of bad things could happen. The two threads could each do this assignment statement, writing and then overwriting the last slot. One of the increments of n might get lost, etc. But by putting it under a lock, we assure that only one thread is in this code at a time, and that the properties we're trying to achieve are preserved here. So the next observation is, well, what if I just put a lock around each individual statement? That wouldn't protect the invariant, which is that there's a relationship between the items array and n. So really you need to put a lock around both statements, because otherwise one thread, you might have two threads racing to getting in between the first statement and the second. So this will again encourage you to figure out what your invariants are. You might even want to have a test that says assert that the invariants are holding, and do that test when you enter the lock and when you leave the lock. In the example so far, we've been locking over this. Every managed code reference type object has a monitor or can have a monitor. And so you often see the pattern that people just lock over the object that is the data structure, in this case, locking over this. In some cases, it's not the best practice, because anyone who has a reference to your object can take a lock on it. So you can't just look at your code and the locks you're writing to be sure that there's no deadlocks. In these cases, to be more defensive, you could have a private field like LK here, and then lock over that amongst your methods. Then even if other objects have a reference to your list, touching your lock won't affect the correctness of your code. Another pattern we see is for people that are writing a lock over a static method, is that they'll lock on type of their type. And that's not a great practice either, both for the kind of denial of service reasons that I just gave, and because things like types and strings can leak across app domains, and if there is an app domain unload in another domain, your lock may not be unlocked, etc. So again, it's better to have a private static object for your static locks over your type. While you're holding a lock, it's dangerous to call other third-party code. You don't know what it's going to do. Even if you test it today, you don't know that the next revision of that library won't do something different with respect to locks. He may do something where he may block, and now your lock is held for a long time, and your clients are having trouble. It's better to get out of the locked scope and then do your callbacks or your down calls. When you are using locks in your code, you really want to pick the right lock granularity. And this comes back to that safety versus liveness versus efficiency story. So here with this type, I have one single lock in this first version. And anybody who calls into my service will be serialized on that one lock. It might be safe to allow different instances of this service to concurrently run under their own locks. So another thing you could do is for the instance methods, do1 and do2, they could lock over a per instance lock. Maybe there's even an opportunity to do operations 1 and 2 concurrently. Maybe we could add another lock. Well, now you start seeing the tension between getting more concurrency and remaining correct. And I guess my guidance is to not add more locks then you can reason over clearly. Don't add locks unless you clearly need them for some concurrency benefit. Now, in a program that has more than one lock in it, there's a possibility of having a blocked lock cycle graph. So here, in an oversimplified example, if my service has two resources A and B, and it does things that ultimately end up locking A and B, or on this other code path, B and A, that can lead to a deadlock. You can avoid this kind of problem by defining an order between the two locks, and then always making sure that you acquire the locks. If you're going to lock on A and B, always acquire them in that same order. So these are the key rules for thriving with locks in managed code. I'm also going to talk briefly about how to use the wait facilities. So here I have a channel that might be used to exchange a piece of work between a producer and a consumer. And in this code excerpt, we have some data item T. We have a flag on the channel, which indicates that it's full. And we have a monitor that we're going to use to synchronize all the concurrent calls on get and on put. So here, if someone calls get under a lock, we're going to test whether this channel has an item in it. And if it doesn't, we're going to go to sleep. We're going to call monitor.wait. And we know that eventually someone will put an item into the channel, and again under a lock, they will set the condition that there's an item in the channel, and they will signal it using pulse-all. This will have the effect of making this thread runnable, and once this code leaves this monitor, this lock, this other code can reacquire it, retest the condition, find that it's got an item, and then do whatever get does. So the key rule for using monitor.wait is to use exactly this pattern down in green below. So let's look at some of these other ways of writing it. If you tested the condition and then locked, you'd be violating the notion that you have shared state that's accessed not under a lock. And that can lead to any kind of misbehavior. In the next condition here, we're being a bit clever. We're locking on the monitor, and we're saying if it's not full, wait, knowing that when someone else out there puts an item in, they'll wake me up. And then I go to the continuation here without retesting the condition. I figure if somebody wakes me up, it's okay to proceed. But that's not the most defensive practice. There could be several races going on to either put or get items from this structure. So it's safer to test and retest the condition, always under the serialization of a lock. So here's the complete piece of code for that channel that correctly works, I claim it's correct, for multiple readers and multiple putters and multiple getters. We see that even on the get path, having waited for there to be an item to get and taking the item and clearing the full flag, it's still necessary to wake everybody up, to wake up any putters that are waiting so that they can proceed and put another item. Notice that they won't start running until I leave this lock. And then they'll wake up, try and reacquire the lock, retest whether it's full or not, and if so, they'll put an item. If it's not full, they'll put an item in and wake up the other sleeping getters. It's not the most efficient code in that I'm using pulse-all to wake up everybody who's gone to sleep. It would be nicer if I only woke up one putter or one getter, but that code would be much more complicated. So sometimes you're doing a trade-off between simplicity and correctness and performance. Okay, so time for another demo. We're going to write a parallel version of our count primes application in theory. Hibernation, okay. Great. So, before I do that though, remember that I said the easiest way to make your code go faster is to write a better algorithm. And I won't go into the nitty-gritty of it, but I've changed the prime counting algorithm from hideously stupid version to a merely simple, oversimple version. So to test the primality of any given integer, we only test whether all the primes up to the square root of that integer divide into it. And this one does run several times faster than the stupid brute force prime finder. I won't even bother running it, though. Now, to really show you the benefit of writing a parallel version of count primes, I need to take you forward in time to the year 2009 and run this on an 8, or 2010, run this on an 8 processor desktop machine. Now, I'm going to simulate that by running it on an 8 processor machine I have back at Microsoft. So on this machine, we have 8 processors, and they're currently all idling. And first, I'm going to run that better algorithm version of count primes. And we see that for a much larger workload of 10 million, we see that there's one thread that's running full out here. And I'm only getting 13% of the benefit of the CPU of my 8 processor desktop machine. Now I'm going to run the parallel version of this code, and we see that it finished in under 2 seconds. It's about 7 or 8 times faster than the single-threaded program. And we see that indeed we get these little spikes on all the work is run on all the threads. So would you rather be shipping software that ran like this or ran like that? Is the question. So now let's see what I did to this code to make it go in parallel. The first thing I did was I refactored the code, taking all the concurrency stuff out of the UI class. So the UI still runs worker async. It still does a do work, which calls, in this case, a new instance of a primes object to count primes. It still gets notified when it's completed. It still has cancel and so forth. Here in the primes code, when you call count primes, the first thing I do is I build up this improved algorithmic version where I have a table of the primes less than the square root of n. Now that table is going to be used by a lot of different threads. So you start thinking, uh-oh, shared memory. But because of the way I build it, by the time it's seen by the other threads, it's a read-only table. So that's an example of using immutability as a way of safely sharing memory. The next thing I do is I'm going to take this workload and divide it up into units of work of a certain chunk size and farm them out into callbacks on the thread pool. So I call threadpool.queuseRWorkItem, and I push, in some cases, hundreds of thousands of work items into the thread pool. Then I'm going to wait. Each time I do that, I'll increment the number of tasks that I've launched. Then I'm going to wait for all those tasks to complete. While the number of tasks isn't up to the total number of tasks I issued, or while you haven't canceled the operation, I'm going to update my progress and go to sleep. Now let's look at what those callbacks from the thread pool do. First, I needed an object to capture the piece of work, which is compute the primes in the interval, count the primes in the interval m through n. The callback unpacks that argument object and calls this method count primes in range, which is still sensitive to cancellation pending. Once it has updated, once it's finished, it's got to update some shared state. So I've defined some shared state here, notably the total count of primes and the number of completed tasks. And I've documented it's guarded by this monitor. And I've created a private monitor. And I've also documented that my shared read-only state is, in fact, shared and read-only. So now, as each callback completes, it updates this count, updates the number of completed tasks, and it wakes up the monitor. This might have been a pulse or a pulse all. In this case, it doesn't matter. Back here in count primes, as I said, we're waiting until the number of completed tasks equals the number of issued tasks. And when that happens, we take our grand total and we return it, and that will have the effect of being packaged up in a result item and delivered back on the UI thread. So recalling our last diagram, where we indeed started a piece of work with run worker async, and do work started this big count primes thing. The difference here in this case is that count primes ends up firing off a whole lot of items through threadpool.queue user work item into the thread pool's queue. And the thread pool will start up more threads, as many threads as is beneficial, working on each of these little units of work. So we have lots of nice parallelism here, even though I didn't explicitly start up 1 or 2 or 3 threads. After it does this, the count primes code will see is the number of completed tasks less than tasks, and then go to sleep, indicated by the completion of this computation here. Then as each callback completes its work, and in that lock block updates completed tasks and the total count, and then pulses the monitor, it wakes this code back up, and the while condition is tested again and again and again. Each time it does so, it also calls the report %progress, which has the effect of delivering a message and then an event here on the UI thread, updating that progress bar. Finally, the very last work item completes, the while loop exits, we post a result back, and we complete the computation there. So we've met thread pool, and we've met various facilities on monitor, including the lock syntactic sugar. But there are some other really interesting facilities in managed code concurrency that I can't, time will not permit me to go into today. But you might check these out for yourself. In particular, this family of events is actually more powerful and flexible than monitor.wait, but they're a little more complicated to use. There's also various refinements on the async pattern of start this work and then later end, give me a iasync result that I can either wait on or get a callback about. And I encourage you to go read about those as well. These other guys down in the bottom left corner are more advanced, and they're not necessarily as easy to use, and in some cases they're not actually recommended. So as I was saying before, we'd prefer to use the thread pool over explicit thread management, because over time the thread pool will just get better and better at adaptively running your work. And as we saw in the first example, rather than using thread interrupt to cancel the work that's going on in another thread, it's simpler and safer to set a flag like cancel pending and have the work thread pick up that fact and leave in an ordered fashion. If you do a thread.interrupt on another thread, it might generate an interrupt exception that your code is prepared to handle, but you might also be in some third-party code where that interrupt isn't expected. So polling for cancellation is safer. Okay, in the last part of the talk, I'm going to talk about some ideas and some work in progress for evolving the Microsoft concurrency programming models and platform and libraries and tools to make it easier to, I have a question. Can I take it at the end? Thank you. So if you grew up in the industry, you remember this terrific phenomenon that the software you shipped last year ran faster on this year's computers and even faster on next year's computers. And we'd like to reestablish that relationship, even though an individual core isn't necessarily running a lot faster next year, but we have more cores to take advantage of. Now on the server, that seems relatively straightforward, because we already have server programming models that can harness more and more and more cores, because we can just give more client work to more threads. On the client, it's a little less clear, because the client is doing one operation at a time, and somehow you've got to apply a team of 4 or 8 or more threads on that one operation to speed it up. The vision for what we'd like to do is to try and do for concurrency programming the things we did for automatic memory management when we brought out the CLR. So In doing so, we eliminated whole categories of bugs, and we boosted your productivity by doing a lot of things on your behalf. And you know, the self-tuning automatic CORGC can certainly rival a lot of individual memory management code. So the idea of the vision is this. We'll evolve our languages with new libraries and new concurrency facilities that let you express more latent parallelism in your code. So even if you're shipping on a one processor machine today, there's this latent parallelism that can be exploited later when a machine ships with more and more and more cores. So on new hardware, we would automatically apply that extra hardware to the latent parallelism that you have. So maybe we schedule more tasks at the same time. We farm out your loops to more worker threads, etc. The real challenge to this is finding a programming model that lets you do it without having latent data races or deadlock bugs. Sometimes you'll ship code, you'll test it on a one processor machine and it works well. When you actually have 2 or 4 processors, you'll find new bugs. So we're in search of new programming models that don't manifest that latent bugs, even though it does represent latent parallelism. Some of the products we are shipping and working on, and some ideas I'm going to talk about on this slide. In Visual Studio 2005, we have this OpenMP feature, which lets you take your C++ loops in native or managed code, add some pragmas around them, and farm out the work to many parallel teams of threads. There's a really great article, as I mentioned, in MSDN this month. Herb Sutter is going to be talking about extensions to C++ for concurrency that he's calling Concur. And there's a session on that later in the week, on Friday, I believe. Today we saw the extremely cool link facility for bringing into your, for uniting both relational XML and in-memory sets and sequences of data. And it occurs to us that in the same way that you can farm SQL out to a parallel query optimizer on a server, down the road you may be able to use those same higher order link queries and do some parallelism implicitly in your client code. So we're not announcing, or we don't have anything to show about parallelizing link yet, but it's very attractive, and I think it will allow us to raise the abstraction level of our manipulations of tables. On Friday, there's a talk from Tim Harris of Microsoft Research on 5 different areas of investigation that MSR is doing about concurrency. So there's a couple that helps you succeed with locks, either checking your lock usage to make sure you're not sometimes locking an object and sometimes not, or declaring what your lock constraints are. And there's a talk on a messaging style of asynchronous function calls called C omega, transactional memory that I'll talk about in a moment. And we're also looking at Haskell and doing implicit parallelism in Haskell. He'll be talking about those. The next slide I have will actually talk about this concurrency and coordination runtime that's a project that the team that I'm working on is doing. The idea of this CCR is a local, it's an experimental local message passing runtime for building very highly concurrent federations of tasks to work on something. All the communication between the tasks is by posting a message on a port of another task. You respond to that message by installing, that is activating, a message handler. And the message handler can act on a message or a certain pattern or join over a set of messages or an infinite sequence of such messages to invoke a handler that does some computation. There are ways of using this library to program without locks and still get, part of it is programmer discipline to maintain memory isolation, and part of it is higher order declarations to control the amount of concurrency. And I'll show you this, I have an example here. The same counting primes example. First, we'll need an object to represent a work item. And so we have the lower and upper bounds of the interval and a port that we're going to post the result of the computation on, the count of the primes in this interval. And now here's the whole program for running these work items. So count primes is called with a maximum integer to run up to and a chunk size, and a port to report the total upon. And then it has two private ports. One is the queue of work items, and one is a port that accumulates all the result counts. This code then uses the post library method to create new work items and post them on this work port. Now, if you didn't do anything else, what this would achieve is queuing up a lot of work and nothing happening. So you also have to activate a handler that on this port, whenever a work item arrives, you do this code, which includes counting up the primes, and then posting on that item's result port the count that we've seen. And finally, we also activate a handler which fires just once, which says after you see n divided by chunk size result messages, fire this handler with the array of range counts. And it then adds up those counts and posts as a final result the grand total. So that's a flavor of this concurrency and coordination runtime. If you want to read more about it, there's a link here. It's, we just posted a description up on Channel 9. Another really promising technique is software transactional memory. In the previous section where I showed all the rules for succeeding with shared memory and locks, we see that that adds a lot of extra complexity to your code. I used to say shared memory plus locks equals bugs, but I thought I'd better just say extra complexity. So the problem with this is that simple mistakes, small failures of discipline can lead to data races or deadlocks in your code. And it's particularly a problem if you're writing software components that are going to be running concurrently and you still want to compose them. So separately authored components and concurrency is a real challenge. The great idea about software transactional memory is to apply all the great ideas of transactions for those ACID properties, except durability, for in-memory objects. So in an STM world, you might just say atomic, open brace, and then your computation. And you know that while your code is running in that atomic scope, any data that you touch is isolated with respect to the other threads. You didn't have to go and figure out what data might be shared or not shared. You just use your data. The engine of the STM has to observe all the reads and writes that your threads are doing and the other threads are doing, and figure out how to schedule that so that they're serializable. In some cases, you would have to abort and retry one of these blocks if two threads both simultaneously updated and read some variable. So the beauty is that your code, while you're running in this atomic scope, your code thinks, I'm the only code on the machine. The other nice thing about this is you can use it as an error cleanup mechanism. So if you already have the mechanism that lets you retry and undo and restart the work, you can also use this as a way of just saying, oh, I want this all cleaned up. I'll throw an exception out of this atomic block, and it'll all be cleaned up. So I've seen some experimental code which was 1/3 concurrency control locks, 1/3 error cleanup, and 1/3 user logic. And the first 2/3 just go away and just have just nice user logic. So it promises some great strides in programmer productivity, this transactional memory. Unfortunately, it's still in the research stages. It's like automatic memory management 5 years before the Java VM or the CLR. We have things to work through about how this interacts with I/O and how it interacts with various other features in the managed code platform. So to conclude the talk, concurrency, I believe, is becoming more important for both responsiveness and parallelism in our code, particularly as the kind of hardware we run on evolves into processors that don't go any faster, but we have more and more and more of them. We're going to continue to evolve our platforms, libraries, and tools to take advantage of this, make it easy to use. And you now know some of the key concepts and rules for working with shared memory, with multi-threads, shared memory, and locks. So I encourage you to go try it. Try taking some of your code and farming it off to the thread pool. Some key resources for you to look at if you want more information. Herb Sutter had a great paper in Dr. Dobbs' journal at the start of the year. Vance Morrison had 2 fantastic articles in MSDN, What Every Programmer Needs to Know About Multi-Threading, and an article in MSDN this month on the sticky problem of memory consistency models. I didn't have time to go into the asynchronous pattern, and I encourage you to go learn about that. Andrew Burrell, who's a Microsoft researcher, has a very nice paper on programming with threads in C#. And I claim that the best book for learning about managed code, threading, design patterns, and usage is actually Doug Lee's book on concurrent programming in Java. 95% of the information in that book applies to managed code. And if you read that, you'll get some really interesting new insights into the problem. And finally, if you go to the Intel website and you look up Platform 2015, you'll see some very interesting ideas from Intel about where chip multiprocessors may go in the long term. In terms of related talks here at the PDC, in the session right after this one, there's a talk by Joe Duffy, Programming with Concurrency #2, which will drill down more into the low-level guts of how managed threads interact with OS threads, interact with the message pump and with COM, low-level memory consistency model stuff, etc. It's more of an under-the-hood talk. Rico Mariani has a talk on writing faster managed code, which I encourage you to go check out. There's a talk tomorrow on Link, which I think is the coolest thing at the show. Tim Harris's talk on the 5 Microsoft research concurrency initiatives. Herb Sutter's talk on C++ future directions and Concur. And there was a talk in the last time slot on our high-performance cluster computing stuff, which is also relevant for some of you. Joe and I will be at the Ask the Experts session on Thursday night at 6:30. And so that's the end of the talk. I'm happy to take your questions for a few minutes. And I encourage you to also fill out the speaker evals. Thank you very much.
Yeah, I guess so.
Is there a microphone for questions, or? Back one slide.
Hello?
Are there, yes, is there a question?
Yeah, right here.
Okay, wherever you are.
Right here. So the thread pool,
Yes.
one thing that's been frustrating is, first, there's only one, right here.
Yes, sir.
Only one per app domain. I can't limit the number of threads on it, so we make the assumption that, I'm not going to be invoking any other threads or some third party or some Microsoft, component like calling a web service is going to invoke another thread, and then I'm going to run out of threads. Why don't we have that capability? And is that going to be changed in the future? I mean, it seems like everyone's had to write their own.
Well, whenever I don't know the details, but I'll speculate.
Okay.
So the first comment is that there is a way to control with very coarse knobs some parameters on the thread
besides
pool,
machine
right?
config. Yeah.
No, but I mean, you can set the maximum number of threads that it will start up times the number of processors and so forth. But it's clear that that's not meeting your needs.
Right.
I believe that the thread pool is meant to be a general purpose, easy to use facility, and in any part of the .NET framework, there's always a trade-off between this ease of use thing and this nitty-gritty control for the guy who needs every knob. I'd be happy to capture your suggestions and feed them to exactly the right people if you'll come and see me in about 5 minutes.
Okay, then one other question.
Yeah.
You made a comment that you can always assume that you have code that ran on last year's computers is faster on this year's computers. And I don't know the technical difference between hyperthreading and multi-core, but logic dictates if a computer is running at 100% versus 50%, the one running at 100% is going to be faster. And I guess the best example I can have is, we use init, and that's a single-threaded type of, operation, and I'm assuming the C# compiler is. So if I'm on a non-hyper-threaded CPU, let's say running at 2.8 gigahertz, and all of a sudden I throw it on a hyper-threaded 2.8 gigahertz
Yes.
system, I'm running at 100% versus 50%. Where does that leave me? I mean, are we really saying that hyper-threaded is running just as fast at 50 versus 100?
Yeah, a couple of comments. First, Intel's initial implementation of hyperthreading in the Pentium 4, I forget the code name of the processor, left some things to be desired. It was a very interesting first step into multi-threading or hyper-threading, and it certainly caused everyone to think through how does the OS represent this, and so you started to get notions of logical processors and so on. I think over time you'll see multi-threading implementations that actually give you a bigger performance boost. For some workloads, hyper-threading was a 15-20% speed up, and for other workloads, it actually slowed it down, depending on subtle interactions between various little bits of the microarchitecture. So the metric about 50% of a dual-core hyper-threaded thing versus 100% of a non-hyper-threaded thing isn't really the important metric. It's kind of the wall clock time is the issue. I don't think I answered your question, though.
Okay. I don't know. I never timed it, but I mean, I felt like anytime you have any math-intensive operations, like maybe what you're doing there,
Yeah.
and you haven't thought through parallelism, you could run that risk of all of a sudden taking out that ran fast on a slower technology, an older technology. It's now going to run slower on that newer one.
In the more recent processors, where they have actually two physical cores and they have fully replicated machine resources for everything about between the processor pipeline and the caches and so forth, you're seeing for code that fits in the cache more like a predictable doubling of speed.
Okay.
Whereas in hyperthreading, you are sharing a lot of the bits of the processor pipeline.
Right.
And
Okay.
so sometimes
So we could equate multi-core to more multi-processor, where hyper-threading was kind of like a wannabe solution then, right? Would that be?
Yes, I think that's fair.
Okay, thank you.
Yeah. Okay.
The question I have is, if you're working in an environment like ASP.NET that may throw like a thread abort exception, an asynchronous exception, is the C# lock keyword a safe thing to use, or is there a better construct?
Well, it will end up unlocking the monitor, right? When you leave that code because of the finally that's under the hood there.
But doesn't it call monitor lock before it enters the try block? And
Yeah, yes, but the finally will release the monitor on the way out.
But if a thread abort exception is thrown between when you call monitor lock and you enter the try block, the finally block won't be called, will it?
I don't know, honestly. Yes? Okay. So this gentleman just concurred with your statement that that is an issue. Again, it underscores, if you can, to try polling for cancel rather than the thread abort, the thread interrupt. I don't know.
I was just wondering if the lock keyword was safe to use in C#.
It's my understanding that it is, but I may not be correct. Does anyone else have an opinion? No. Okay. Is Joe Duffy here? Okay. Yes, sir.
Just a quick question. I remember being maybe 20 years ago in what seems to be almost the identical talk. The Moore's law is running into its physical limits. We have to go to parallelism. The Japanese government, did the 5th generation project, and everyone was talking about, Sequent made Unix with 8 processors. Everyone was talking about, huge arrays of small, simple processors talking to each other through 4 ports, kind of the one that you talked to before. Can you kind of compare then and now, and what changed in a way?
Well, one thing that was different in the past, if you just waited, you would be able to find a uniprocessor that would be faster than the expensive engineered 8-processor Sequent or what have you. And to the extent that the clock frequencies aren't going to be scaling up quite so fast, you may have to wait a long time for the 6 gigahertz processor compared to taking advantage of the 4 or 8 core 3 gigahertz processor. So that's how I rationalize it to myself, that we are not going to continue to see the clock frequency scaling, and we're going to have to kicking and screaming against our will, learn to write more concurrent software. There's also an interesting observation that once you start doing the interprocessor interconnect on the chip and you integrate all the other things into the system on a chip, you've really removed all the extra cost. Those old servers were very expensive because they had very expensive interconnect fabrics that were one-off custom things. Once these become commodity parts from the CPU vendors, there won't be such a price differential to have the multiprocessor on your desk. Next question.
Sure. Is there any talk or any plans about making thread pool and your threading model, making it POSIX compliant? I have some portability issues. I have to port to a number of different platforms.
I'm afraid I don't know anything about that.
All right.
But if you see me afterwards, I'll take your card and I'll put you in touch with the right person.
Sure. Thanks.
You mean like Mono? I don't know what Mono's thread pool implementation is. I still doubt it's POSIX. It relates to POSIX. Is this like POSIX P threads? Okay. Next question. Over here.
Yeah, in your second example, would you have recommended as best practice to declare some of your shared state as volatile in case somebody else came along and wrote code that would be optimized by the compiler and taken an old value that it was caching locally?
In the parallel example, or
in the parallel example where you had the count of the primes.
All of those values were manipulated under a lock, which is I'm trying to give very simple rules to follow, and I think if everyone manipulates their shared memory under a lock, they don't need to resort to the volatile problem. And the trouble, or feature, the trouble with volatile is it lulls you into a false sense of security that you are getting the correct serialization of access to the data.
Right, but for another method, which is just purely reading the variable,
Yes.
they could, for example, be in a loop,
Sure.
and then they cache the value, and they keep printing out 4 when it's in fact 2,000.
Right. It certainly will work there. For people that are even going to contemplate using volatile, I'd want them to read more about lock-free or low-lock kind of programming, such as Vance Morrison's article at MSDN this month, because there are a lot of gotchas around it.
Okay. By the way, I wanted to thank you for a really good talk. That was I thought, a very measured introduction into why the world is going multi-core, which I thought was a much more rational explanation compared to a lot of the marketing that I hear from people saying, this is just a much faster way to be processing without realizing that there's a huge programming burden once you go to concurrent programming models.
Yeah. If you think about it, let's say that Moore's law suddenly stopped, right? The whole industry would have 10 years of speed up still, tuning up all the code that they've shipped in the past, which had performance issues in it, as a coda to that comment.
Thanks.
Yeah, thank you very much. Yes, sir.
I want to just step back and ask why threads as a way to parallelize work. So other systems like Unix, for instance, prefer running multiple processes to solve the same problem where you don't have as much shared state that you can corrupt if you're not careful.
Well, you're free to still use multiple processes and enjoy the address space isolation of the processes. And Microsoft, in all kinds of different problems, they'll either choose to use a multi-threading shared memory or a separate address space approach. When you are sharing lots and lots of data, because there are threads that are each contributing to bits of a result, I don't think that you can get that result with processes unless you use, again, a shared memory primitive to open up a shared memory between the processes. So the same facilities are available in Windows, but the way we tend to write that stuff is to use lots of threads. I'm not sure in the Unix world they don't use lots of threads for those kinds of computations as well.
Right. It seems in Windows there's more push toward using threads as opposed to using processes.
That may have to do with the overhead of processes on Windows. I will go further than that. Yes. Sir.
Yes. Hi,
last question, I'm afraid.
Okay. So there was a recent article I read in MSDN that was very good. It may have been one of the ones you mentioned up there. I don't remember. And if I understood the summary of it, it was recommending very large-grained locks.
Very large?
Large-grained locks as opposed to fine-grained.
Yes.
Do you agree with that in general?
No.
I mean, the article, of course, goes into a lot of detail about why.
There is a cost to monitor enter and exit or to using a lock. Under the hood, they end up using interlock compare exchange instructions, and they are like 100 cycles, 100 times more expensive than an add. So to the extent that you have very fine-grained locking, such as was in my example where I'm locking to do 2 adds, the bulk of the cost is going to be in the locking. But it's still, I'd rather have a correct program that loses a few percent to the locks than a incorrect program that doesn't. If everything is fine-grained updates through locks, you are going to get a performance penalty, and you may have to restructure your data to try and use one lock over a larger set of shared memory.
Okay.
So there's a trade-off. I don't necessarily agree that great big chunky code under a lock is a good idea.
Okay, thanks.
Thank you.
I got a quick question.
Okay.
On the feature research that you had spoken about, is some of that bringing in work done by Dr. Schmidt on the ACE, using the leader-follower leader pattern or leader-follower pattern?
I'm sorry, I've not heard of that.
Okay.
Happy to talk about it, though. Okay. Thank you very much for coming.